All right, we're going to start chapter 7 today, and the first part of this chapter is going to be a discussion of different types of radiation. We call them electromagnetic radiation, and radiation just in general is a way that energy can travel through space. And you see listed here are the different types of radiation that we have, the electromagnetic radiation going all the way from gamma to radio waves. And the reason we care about this is because you can use those types of energy for various things. So notice that X-rays is on there. You can use that to take images of your body, so like the broken bones that you may get. Microwaves are on there, so you can use those to cook your food. Radio waves we can use to listen to the radio. Visible is what we used to see, so it's the different colors that we see. So all these types of radiation are incredibly important in our lives. So let me just go through a few of these terms first, and then I'll show you how to do some of these calculations. The first one is wavelength, and wavelength is exactly what it sounds like. It's the length of the wave, so it's how far the distance from one peak to another peak is. So if you see my little picture there, notice that the first picture has a very short wavelength, and the second picture is a much longer wavelength. And the data table that I have there is the wavelength increases to the right. That's what that right arrow is showing, is that as you go to the right, this one would have the biggest wavelength. There we go. And then gamma would have the smallest wavelength. Notice that frequency and energy are inversely related. So as you go to the right, frequency decreases. And frequency is kind of hard to draw. You can't really draw a picture of it because it involves motion. Frequency is how many peaks pass a given point in a second. So if you stick your finger out and the wave is passing by your finger, however many peaks pass by your finger in 1 second would be the frequency. So if you can imagine those two waves that I have drawn, the shorter the wavelength, the more peaks will pass by in 1 second, which means the higher the frequency. So they're opposites. As wavelength decreases, as you get shorter, the frequency will increase. And so they're inversely related. And the same thing with energy. However, the speed of these are actually all the same. So the speed is the same. We call it the speed of light, but it's actually the speed of any of these radiation types. And it's about 3 times 10 to the 8th meters per second, which is incredibly fast. We've never achieved the speed of light. And there's a lot of theory, if you ever take a physics class, about what would happen if you do achieve the speed of light. We've done the speed of sound, but we haven't quite gone the speed of light yet. So these are the variables, and just as a side note, this chapter is going to have a lot of variables, a lot of constants, a lot of equations, and a lot of plugging in and calculating things. So what I want to encourage you to do is to watch your units, make sure that as you're plugging things in that the units work out the way you want them to, and make sure you're familiar with what these variables mean. So wavelength is kind of an upside down Y. It's called a lambda. It's a Greek symbol, so it's kind of a fancy upside down Y. And like I said, it's the distance between two peaks, and it's going to be any unit of length, just like how if you're measuring the length of your table, you would do meters or centimeters or millimeters or some unit of meters. And so usually it's going to be meters. It also could be nanometers because some of these are so small that we use smaller units for them. Frequency is kind of a fancy V. It's like kind of a combination between a U and a V. And this is the number of waves, like I said, that pass by a given point per second. And so you're going to have several different units you could see for these. A hertz is the same thing as a 1/second. And another way to write that is seconds raised to the -1. So all of these are the same thing, and these are all units that you can use for frequency. Speed is going to be the speed of light, which is a constant. So they're never going to give you this information in the question. They're never going to ask you for it because we already know what it is. They expect that you know to plug in C, and it is in your reference packet. And this is in units of meters per second. So notice that if you're using meters per second here, let's say you're plugging in wavelength and they gave you the wavelength in nanometers, that's where you have to watch those units and make sure that they cancel out. So here's another picture of long and short wavelength, a little better than the picture I have. Notice that it's opposite, that if you have a long wavelength, you're going to have a low frequency, and if you have a short wavelength, then you have a high frequency. So in first year chemistry, all you had to do was understand these the relationships, but now we're actually going to calculate them. So before I go through some of these calculations, let me just make a side note. This is in Canvas. If you want to get a clearer picture, it's kind of blurry with the way I had to post it in here, but I just listed out all the different variables for this chapter, the units that you might see for them. There's some conversions over here that you might be helpful to you. All the constants are there. So speed of light, we're getting ready to do Planck's constant. In your homework, numbers 45 and 47, you're going to need this information, which is in the book, but it's just annoying to have to try to find it. So I just listed it for you there. there. And then we have a whole bunch of equations as well. Some of them we can combine, and I'll show you how to use all of these. And what I did is I highlighted the ones that are in your reference packet, and so those are the ones that you're probably going to see on the AP exam. So notice that the ones that are highlighted in yellow, those are in your reference packet. And all of that is in Canvas if you want to get a better image of it. All right, so here's some relationships. We have this first equation where we have wavelength is the upside down y times the frequency will give you the speed of light. We know what the speed of light is, so if they ever give you wavelength or frequency, you can just plug it in here and get the other one. Again, just watch those units and make sure the units are canceling out. Here's a few more. So we have Planck's constant, which is also in your reference packet. And this one is going to talk a little bit about the energy that's transferred in packets of energy that we call a quantum. So quantum is singular, quanta is plural. And there's a lot of vocab in this chapter that you might want to go through, and just make sure if you read the chapter, it'll go through and explain some of these as well. Energy is quantized, which is a fancy way to say that it only occurs in discrete units. So it's not like a spectrum. Like if you picture a color spectrum that goes from white all the way to black with gray in the middle, it's not a spectrum. It's like there's cutoffs where it can only exist in certain units. Einstein did a lot of work with some of these energy relationships. So he was able to study a stream of particles called photons. Again, lots of vocab for this chapter, so reading the chapter will definitely help you. And he was able to figure out that the energy of a photon is equal to Planck's constant times the frequency. He can plug in other things, and we get some more equations. And again, these are all on the list of equations. He also figured out this famous one that I'm sure you've heard of. If anybody says, tell me a science equation, that's usually the first one they think of, although most people have no idea what it means or what the letters mean. So energy is the E, M stands for the mass, and C is the speed of light. So this is showing you that you can convert mass into energy, or you can convert energy into mass. You can't create or destroy either one, but you can turn one into another. And again, for number 45, you're going to need the mass of the proton, and for number 47 in your homework, you're going to need the electron. So you'll use these two in your homework. And we've got some more description of how light travels. So it travels through space as a wave, but it also transmits energy as a particle. And so which one is it? Well, it's both, which is really hard for us to imagine, because usually we think of either waves of energy or particles as little spheres bouncing around. And it's actually, they behave as both. So we say that it's a dual nature, that it can be a wave or a particle, which I know is hard to wrap your head around, but you just kind of have to accept that they are both. And you'll study this a whole lot more in physics if you ever take physics. So we have more equations down here, but be careful with this one. So this V right here is different from the other V. So we have this fancy V is frequency, and just a plain old straight V is this velocity, or the speed of it. So just be careful, those are two different things. Frequency is 1/2, and the velocity here would be in units of meters per second. But again, you want to make sure your units cancel. So if your wavelength is in meters and you have meters per second here, that's what you're looking for. And then H is going to be in joules times seconds. So again, velocity needs to be in meters per second if you're going to use Planck's constant. Like I said, all matter exhibits both particle and wave properties, which is weird for us, but you just have to accept it's the dual nature of what we've learned. This leads us to hydrogen. So they focused first on hydrogen when they were studying all of these energy transitions, because hydrogen is the simplest of all the elements. And so they're able to really focus on it. And it does get way more complicated when you get into different elements, but they were able to learn a lot just by studying hydrogen. So notice that the bright line spectra of hydrogen has only certain colors. And we did this in my honors class if you had me at the beginning of the quarter, which everybody did last semester if you had me. This is where you put on the weird kind of glasses, and I was able to shoot electricity through a glass tube that had hydrogen in it. And what you're able to see with the glasses is certain colors. I don't know if you remember doing this, but those colors show you the spectrum of hydrogen. So we can identify that it's hydrogen based on those colors. And really what we're doing is exciting the electrons. So if you just picture the atom as a circle, even though it's not really, if you have electrons, when you give them energy, they can go to upper level energy rings, energy levels, but they're very unstable, so they're not going to stay there very long. Eventually eventually they'll come back down. And as they come back down to ground state, they release energy. And if it happens to be in the form of visible light, then you can see it as colors. And that's what we were able to see. This was also from the Flame Lab. A good analogy that I've heard is if you go to the gym, so like if we were, not a gym that you work out at, but like the basketball gym at school, I would do this with you if we were in school, but if you take a bucket of tennis balls in the gym and you throw the tennis balls up into the stairs, notice that the tennis balls will only land on certain stairs. They won't land halfway between the stairs, and it's the same with electrons. They only exist in certain regions around the nucleus, just like the tennis balls will only land on certain stairs. To get them to move up the stairs, you have to give them energy, and they release energy as they come back down the stairs. Also, the higher they go, the more unstable they're going to be, and the more likely they're going to fall back down. So all of that kind of relates to these electron transitions. And also, that's the science behind fireworks. So next time you see fireworks, that's the same thing, is that what's happening is the electrons are getting excited and moving to upper levels, and then as they fall back down to ground state, they release energy that you can see. We have some more equations right here. Some of these are just algebra equations, so notice that the C, we talked about this. So what you can do is replace some of those variables. So if you rearrange this equation for V, you can plug in C over lambda, which is what they did here. So it's just rearranging the equations that we did up there. All right, just a couple more things for today. These are the different energy transitions for hydrogen. So notice that they call it different series because they all end on the same energy level. So like some of these are just purely visible light, or the different types of radiation. And the last one is that we can calculate the energy involved for electrons to go to different energy levels using this equation down here. And first of all, Bohr is the scientist who studied the electrons existing in regions. So up until Bohr, they just kind of had the electrons as a soup of negative charge around the nucleus. And Bohr is the first one that first started to organize them into energy levels. So we're going to get to an equation down here that you're going to use more often. This is just kind of an explanation for what's happening. And then as we get down here, this is the equation that we're actually going to use for this. So this is going to allow you to calculate the difference in electron jumps. So as an electron moves from one energy level to another, you can calculate the energy involved using this. So the lowercase n stands for the energy level. So notice that you're going from the final to the initial, and it's just 1 over the final 1 squared minus 1 over the initial 1 squared, and then multiplied by that constant. Notice that there is a negative right here, and that negative means that the energy of an electron is lower when it's closer to the nucleus. As you move away from the nucleus, it's at a higher energy state. And so what you can do for this is if I say calculate the energy that an electron releases as it goes from energy level 3 to energy level 2, you can plug that in. So the final one would be 2, you plug in that, so it would be 1 over 2 squared minus the initial would be 1 over 3 squared, and then you multiply all that by negative 2.178 times 10 to the negative 18th. So if you just plug in the energy levels, you can calculate the energy there. Notice down here you need to be able to talk about what it means. So if the final energy level is a bigger number than the initial, then that means that you're absorbing energy. You have to gain energy to move away from the nucleus. And if it's losing energy, then it's going to a closer energy level to the nucleus. However, the final thing is that this model that we studied with Bohr does not work for any other atoms other than hydrogen because it does get really complicated. So he was able to come up with a simple view of what's going on and kind of a discussion of electron transitions. But because most atoms are way more complicated than hydrogen, so you know how most atoms don't just have spheres, they also have peanut-shaped orbitals that look like these. They have double peanuts that look like clover leaves. They even have ones that look like this, and we'll get into this in another chapter, or in another section of this chapter, actually. But the point is that we can't apply this to all atoms, but we can learn from it. And what you're going to do today is a whole lot of calculations with these, again, that I listed in that summary sheet. So make sure that you have this easily available and make sure that you watch those units. If you're getting an answer wrong from the back of the book, it's probably because somewhere along the way you need to convert your units to make sure that they match. And that's it for today.